Hello everyone. In this lesson we're going to learn about more applications of right triangles. We're going to be mostly discussing bearing. We'll also learn about a method from surveying called the Subtense Bar Method. Most of you have probably heard the word bearing. Bearing refers to the direction of motion of an object, such as a ship or an airplane, or the direction of a second object at a distance relative to the first object, right? We will discuss two methods for finding bearing. The first method uses only a single angle and nothing else. And that angle will be between 0 and 360 degrees. And it's always measured from due north. The second method is going to use an acute angle, which means not that wide of a range. It's only going to be between 0 and 90, and it's measured due east or west of an imaginary north-south line. We'll see what that means when we get to them more clearly. We'll start with the method 1 that we discussed. This method is going to use a single angle between 0 and 360 degrees measured from due north. So when a single angle is given, it is always understood that bearing is measured in a clockwise direction from due north. So this would be a bearing of 32 degrees. And that's all you have to say. You just say 32 degrees. And we know that first you're going to make a north line, right? And due north, and you're always going to measure in the clockwise direction from there. All right. Now, this is not to be confused with the fact that clockwise always means a negative measure and all that. No, here we're just talking about the size, right? So we're dealing with positive numbers when it comes to bearing. So this here would indicate a bearing of 164 degrees. So again, we have a due north line, and then from there we measure 164 degrees in a clockwise fashion. Here, this would indicate a bearing of 229 degrees. Again, you have your due north line, and then you measure from there in a clockwise direction, okay? And this would be a bearing of 304 degrees. Each of the two methods have their own benefits. The benefit of this method is simplicity. All you need to mention is a single number, which is a degree measure. And that's nice. For the other method, the nice thing is that you're only dealing with a acute angle, which is much simpler to visualize, right? But this one, you may be dealing with really large angles like these two, but you're only dealing with a single number. So here we'll look at an example that utilizes the first method of defining bearing. Radar stations A and B are on an east-west line. That's an east-west line. Here's radar station A, here's radar station B. And they're 3.7 kilometers apart. So we know this distance here is 3.7 kilometers. Station A detects a plane at point C on a bearing of 61 degrees. So here's station A. From that point, you're going to draw a northbound line or a ray. And from there, you will measure 61 degrees going clockwise. And station B simultaneously detects the same plane on a bearing of 331 degrees. So at B, you draw a north ray, and from there, you measure 331 degrees clockwise. And now, so that forms the picture. Sometimes this picture is not given and you'll be creating it yourself. So as long as you understand this, you should be good to go. Find the distance from A to C. That's what we're finding, okay? Which we will look at now. Now, because this is an east-west line, right? This northern ray is going to be perpendicular to it, right? So that makes this angle in here a right angle, right? So if this is 61, that means the angle here is going to be 29, right? Now, this angle here is 331 degrees, which makes this small angle here basically 360 minus 331 degrees, which is 29 degrees as well. So that's 29 degrees. Again, we have a perpendicular situation here. So you can see how this angle turns out to be 61 because it is just 90 degrees minus 29 degrees. Of course, notice these are all information we have to find. You know, the image in a homework or test situation would normally not show all those angles. So we get 90 minus 29, which is 61 degrees. So now we know that this other angle is going to be, C is going to be 180 minus 29 minus 61. That's 180 minus 90, which is 90 degrees. So that's why we have the mark of a right angle here. And remember, we are looking for B, the length B, which is AC, the same as AC. The length of long line segment AC. So of course, we have options here, right? Different ways of approaching it. One easy approach is to use a trigonometric function that deals with an angle, the side adjacent to it, and the hypotenuse. So let's bring back our friend SOHCAHTOA. So which trig function is it that deals with an angle, the side adjacent, and a hypotenuse? You see right there, it's the cosine. All right, so if I set up the cosine of 29 degrees, I know that that's going to be adjacent over hypotenuse. Notice that for 29 degrees, adjacent side will be right there, so it's B, over the hypotenuse, which is the side opposite the 90-degree angle, which is 3.7, right? So now if I throw 1 beneath this and cross multiply, I get B is equal to 3.7 cosine of 29 degrees. So we just need to calculate that. All right, as always, we'll make sure our calculator is in degree mode. Once we have made sure of that, we go ahead and type away. So 3.7 times cosine 29, and we get the distance now. So unless there are any rounding instructions, which we don't have, we'll just go ahead and round it to the nearest tenth. So 3.2. So we get approximately 3.2 kilometers is B. Notice I can also write that as AC. Okay, if you put AC and put a bar above it, that's line segment AC. If you just put AC without a bar above it or any other symbol, that means the length of line segment AC. So it means the same as lowercase b that we have here. Okay, so there we are. And that's how you would approach something like that. Make sure you can handle that on your own, and then we'll proceed. All right, so the method 2 of bearing is going to basically use an acute angle measured either due east or west of a north-south line. So you're going to have not just an angle, but you're going to have a direction that you write before that angle and one that you write after it. So when you write, for example, north 42 degrees east, you first draw a north line, right? And then from there, you measure 42 degrees and go in the direction specified. So east would be this way, west would be the other way, right? So here you just go in this direction, 42 degrees, there you have your bearing, right? So again, what's nice about this method is, yes, it's a little bit more complex in that you have to have those directions in there, but you'll only deal with a nice acute angle, which is easy to deal with. Okay, so this one, see, south 31 degrees east. So from here you create a south line and then you go 31 degrees east, so that would be this way, and then you draw your second ray. South 40 degrees west, so first you're going to draw a south line, right? And 40 degrees west, so that would be going this way. Okay, and here we have north 52 degrees west, so from here you draw a north line, and then from there you measure 52 degrees in this direction. All right, and that's that. It's quite simple, except remember, you have to be careful about the two directions. Make sure you're going in the correct direction. Basically, from a north-south line, when you want to go east, you'll go to the right. When you want to go west, you'll go to the left, right? Here's another example. A ship leaves port and sails on a bearing of north 47 degrees east. So you see, here's your north-south line, 47 degrees east, like this. Now, you can draw this bottom part here, or you can just leave it out. You definitely will need the north line since you're going to be going north 47 degrees east, right? For 3.5 hours, it then turns, so it stops here, and then turns and sails on a bearing of 43 degrees, south 43 degrees east. So first you draw your north-south line, and then you go 43 degrees, basically south, and then 43 degrees east, like so. Okay? For 4 hours.
Could you say that again?
That was Alexa thinking I'm talking to her. But anyway, here we go. So, does so for 4 hours. If the ship's rate is 22 knots, which is nautical miles per hour, find the distance the ship is from port. First of all, remember that knot is a nautical unit, okay? The knot is a unit of speed equal to 1 nautical mile per hour, which is exactly 1.852 kilometers per hour and approximately 1.15 miles per hour. So you can see that it's slightly more than 1 mile per hour. Okay, so you can kind of think about it about approximately 1 mile per hour, but just slightly more, 1.15 mile per hour. And that's so that you know there is a slight bit of difference between a regular, terrestrial mile per hour and a nautical mile per hour. All right, so the first thing we want to note is the fact that these two north-south lines are parallel, obviously, right? Because they're both north-south lines, right? And that makes this angle and this angle alternate interior angles with AC serving as a transversal. So those two angles are equal. So notice that 47 degrees plus 43 degrees gives us 90 degrees, making this a right triangle. Of course, that just happens to be very fortunate because we can only handle these kinds of triangles right now, right? So it's kind of a forced situation to give us some practice. Otherwise, rarely in reality would that probably happen. All right, so we will be dealing with more general situations soon. So we do have a right triangle here. We need to calculate this distance and this distance, which we can if we remember our rate time distance relationship. Recall that rate times time equals distance. Now we know that for this leg of the trip, the ship was traveling at 22 knots for 3.5 hours. So if we replace R with 22 knots, which is nautical miles per hour, and multiply it by 3.5 hours, let me go ahead and put the units like this so you can see what happens with the units. Nautical miles per hour, and then times 3.5 hours. Note that the hours will cancel out and we end up with, all we need to do now is multiply 22 by 3.5, and we get 77. So we get 77 nautical miles. Remember, that's slightly more than 77 miles. You'll have to multiply that by about 1.15 to see how many land miles that is. All right, now we also know, so we know that this piece right here, B, which is opposite side B, that's where this 77 comes from. Okay, now to understand where this 88 comes from, we need to see what's happening here. We know that this was happening for 4 hours at the same speed. So if we just set up rate times time equals D again, we're going to use the same rate. So 22 nautical miles per hour, but this time for 4 hours. Notice again, your units should always work out. They should make sense. Otherwise, there's something wrong with the formula. So we get 22 times 4, that's 88 nautical miles. Now remember, we're trying to find C, okay? There is really no need to get any trigonometric functions involved here because we have two lengths of the two legs of a right triangle. We're trying to find the hypotenuse, right? And because that is basically what we're trying to find, the distance that the ship is from port. Notice it starts here at the port, goes here, then goes here. So we want to know at this point how far is it. So we're trying to find C. All we have to do is remember that according to the Pythagorean theorem, leg 1 squared plus leg 2 squared equals hypotenuse squared, right? So therefore we get 77 squared plus 88 squared equals h squared. So h is going to be the positive square root. We reject the negative because it's distance of 77 squared plus 88 squared. So we just have to go ahead and calculate that. So the square root of 77 squared plus 88 squared, and there it is. Now find let's see what rounding instructions we have. None is given, so if we decide to go with two significant digits, we'll go ahead and round that to the nearest 10, and we'll get approximately 120. So approximately 120 nautical miles. And that should do it for this problem. All right, for this next example, we have an observer for a radar station that's located at the origin of a coordinate system. We want to find the bearing of an airplane located at the point 0, -3. And we're going to express this bearing using both methods. All right, so notice that if we're going to use the method which utilizes only 1 degree measurement, we always have to measure that from the positive, well, in this case, positive y direction, which is basically the north direction. So we're going to need to, from there, rotate clockwise 180 degrees, right? So like this, that's 90, and then 90 more, 180. So basically, we're looking at a simple 180 degree bearing using that notation. So method 1, we just do 180 degrees. For method 2, we have to choose a north-south line, right? And in this case, notice that this point here is south of there. So we have to say south. And then which way do we go? East or west? Which one? I mean, if you notice, it makes absolutely no difference. So for this, you could actually use both. So we have two possible answers. If we're going to use the second method, we can say south 0 degrees east or south 0 degrees west. They will be equally correct because you're just saying, hey, it's right below you. It's at the south direction. It's exactly south of the radar station, which is located at the origin. And that's basically how you would approach that. Here we have an observer again, which is located at the origin. And we want to find the bearing of an airplane relative, of course, to this observer, located at the point -5, 5. And once again, we're going to use both methods. All right, so notice that for the first method, where we're going to use a single angle, if we draw this line like this, let's see if I can get my line drawer. All right, so notice that basically we're going to start from the north location, and I mean a northbound line like this, and we're going to rotate clockwise this amount, right? So we need to know how many degrees that corresponds to, right? Notice that's basically almost an entire circle, right? Except how much is that? That's exactly 45 degrees short, because this is on the line y equals negative x, which makes a 45-degree line, angle with the y-axis. So basically this is 360 degrees minus 45 degrees, so we get 315 degrees. So for method 1, we just need to say that the bearing is 315 degrees. Now for method 2, let me get rid of this first. All right, so notice that for method 2, we're going to go with north, right? And then from there, we're going to go this way, right? Which, remember, if you're on the northbound line, west will be to your left. So north 45 degrees west, okay? And that would be it. So that would describe it. So whether you give this method's result, which is 315 degrees, or this one, you'll be describing the exact same bearing, except using different methods. That's it. All right, so for this next example, we're not provided with a drawing, so we're going to have to sketch it ourselves. Two ships leave a port at the same time. The first ship sails on a bearing of 36 degrees at 12 knots. So we're using method 1 here. We're just giving a single angle measurement. So we're going to be measuring that from due north and in a clockwise direction. At 12 knots, and the second on a bearing of 126 degrees at 24 knots. How far apart will they be after 1.5 hours, basically? All right, so basically what we're going to do is we're going to start at a port. We should really sketch the situation, and from there, one ship is going to go basically on a bearing of 36 degrees. So if we draw the due north like that, and then we're going to go 36 degrees, so about so, right? And there we can draw the direction of the first ship, and it does so for 1.5 hours, obviously. And the second ship on a bearing of 126 degrees. So remember, you're going to, this is 30, this right here is, let me get that erased real quickly. All right, so this angle right here we know is 36 degrees. The other one goes at 126 degrees. So of course we're going to also measure that from due north, something like that, okay? And now, because we know it's going to be, notice that if I draw this imaginary horizontal here, right? So if it went this much, that would be 90. So it's going to be a little bit more than that. Somewhere around there, right? All right. Like so. All right, so and this one is going faster, right? The second ship, which is on the bearing of 126, so you would expect it to actually cover twice as much distance as this one, because it's going twice as fast. So we're going to make that longer. Of course, this is all approximate, right? All right. So now what we need to do, so remember, this is 126 degrees. You should really try to sketch this on your own before you watch this. I guess this is a little bit of a late request, but it would be really beneficial for you to try to be, do this on your own before you watch the rest of the video. And that goes with every single problem that I do. So if I sometimes forget to say it, always remember it yourself. You should always try things on your own before you watch the way that I do it. All right. So what we're trying to find is that distance. We're trying to find how far apart they are after an hour and a half. So notice that this angle in here, right here, is going to be 126 degrees, take away 36, right? So 126 degrees minus 36 degrees is 90 degrees, which is helpful because so far we only know how to handle right triangles. This is just good practice for us. And all right, so this ship that goes in this direction is traveling at, so let's go rate 1 time 1 equals distance 1. We're going to calculate the rate for the first ship right here. It's traveling at 12 knots for 1.5 hours. So 12 times 1.5 will give us its distance. So the distance for the first ship is going to be, let's clear all that, 12 times 1.5, so we get 18. That's nautical miles, of course. And the distance that the second ship travels, we can call that D2. This one is going at 24 knots, so 24 for the rate, for 1.5 hours as well. So it should be twice that, right? But we'll just make sure, but it should be 36, right? And of course it is. All right, so 36. So D2 turns out to be 36. All right, so we have the following now. We have 18 here, nautical miles, and we have 36. Actually, we're calculating this one. So that's 36 nautical miles, and this is what we're trying to find, right? This distance right here. So we'll call that just D as the distance between the two ships, okay? So that's going to be easy to figure out now because we have the two legs of a right triangle and we're trying to find the hypotenuse. That distance happens to be the hypotenuse of this right triangle. So we have 18. Let's start with D squared on this side. It'll make it look nicer. So we have D squared equals 18 squared plus 36 squared. So D is going to be the square root of 18 squared plus 36 squared. So all that's left is for us to go ahead and do the square root of 18 squared plus 36 squared. And there we go. So since these other distances are given to us at 2 significant digits, we'll go with 2 here too. So basically 40 nautical miles. Like so. All right. So we are basically
I don't know
done.
that one.
All right, I need to officially shut down Alexa, so I'll be back. For some reason, it's interpreting some of the things that I say as Alexa, so I had to shut her down. All right. So there we go. That's a nice problem. We had to come up with the graphic on our own, but it wasn't that bad, as you can see. You just have to be patient with these, you know, and not give up. I didn't wake up one day and was able to just sit here and just crank out problems like this. No, it didn't happen like that at all. I suffered through many attempts for many years before these became comfortable for me. And if you persevere, the exact same thing will happen for you. And even if mathematics is not your thing, with this kind of effort, your brain will become much more logically trained, and it'll become masterful at handling any kind of logical task that they throw at it. So the reason we do a lot of this stuff is simply that training. You always get the sarcastic student that says, oh, where are we ever going to use this in real life? I'm not going to go sailing. They're missing the point entirely, because the point of all this is not to just make sure that you know how to create these 90-degree situations on the ocean, etc. No, the point is what it's doing for your brain, for your mind, right? The kind of logical development that's happening as you go through it. So that's what you need to be focused on. All right, so that should do it for this problem. Let's go ahead and try one other application and we'll be done for the day. Of course, what I was just mentioning does not mean that this stuff is not used in real life all the time. It is. Those of you who happen to go into engineering, etc., you will actually utilize these things. But and also right now it's only in this section that we're having to deal with these ideal 90-degree situations, because once we learn how to handle general triangles that don't necessarily have to be right triangles, then a whole lot of new situations become available to us that may not have been available before that. All right, so this next one is used by surveyors, and it's called the Subtense Bar Method. The Subtense Bar Method is a method used by surveyors to determine a small distance d, such as the one here between P and Q. And the way they do it is they use what's called a subtense bar with a given length here B, and they situate it so that it is centered at Q, and also so that this bar becomes perpendicular to this line of sight between P and Q. This angle theta is then measured and used to find the distance d. So let's go ahead and find the distance d here with theta equal this angle, notice, to 5 significant digits, and b equals 2.0000. That means they're giving you this also to 5 significant digits. So we're going to try to stick to 5 significant digits for our result as well. All right, so let's go ahead and convert that angle to a pure degree measure for simplicity. So we do 1 plus 23 over 60 plus 12 over, oh, actually, we want to get out of there. So we need to hit the right arrow, plus 12 over 3600. All right, so if we're going with 5 significant digits, we'll get 1.3866, and then we'll round the rest to 7, right? So 2 6s and then 7. So we get approximately 1.386667 degrees, correct? All right, now let's see what we have here. So notice that I could take either the top or the bottom right triangle, and that's all I would need to proceed with solving. So let me go ahead and reproduce the top one here. And we have a little piece like that, and then we connect these. So there we have it, pretty much close, right? So we know that notice that if this entire angle is theta, that means the one inside this triangle will be theta over 2, and so will this one. So we're looking at theta over 2 for the angle. D is what we are looking for, and remember B is 2.0000, so half of it will be 1.00. I'm just going to write 1 because remember, for computational purposes it's just 1, but at the end we just need to make sure we conserve ourselves with 5 significant digits. So that's 1 centimeter, and D is the unknown. All right, and we do know theta, so we know theta over 2 as well, right? So notice that we're dealing with an angle. We want the side adjacent, and we have the side opposite. So if we go to our old friend SOHCAHTOA, you may be thinking about the tangent. You wouldn't be wrong, except remember, that would be good if we were looking for the opposite. But since we're looking for the adjacent, it might be easier if we use the cotangent. Remember that the tangent of a given angle alpha is opposite over adjacent, but the cotangent is adjacent over the opposite. Since I'm solving for the adjacent side D, it might be easier if I have it on the top. So, but either one can be used in actuality. So we get cotangent of theta over 2 equals the adjacent side, which is D, over the opposite side, which is 1. See how nicely that works out? Because D over 1 is just D, so we get D is equal to cotangent. Now we're just going to substitute that for theta of 1.3667 degrees over 2. And now we bring up our trusted friend here. So we go, now of course there is no cotangent button here, right? So all we have to do is simple, just hit 1 over tangent and type that in. So 1.38667 divided by 2. So we get this, and remember we're going with 5 significant digits, so 1 2 3 4 5. Now that this one, because of the 9, is going to round up, so 82.634 centimeters. All right, so that's all there is to that. So notice some nice applications of trigonometric functions here, and these are actually used every day by people in the field. So and of course computers do much of the computation now, but you still need human beings to understand what's going on, right? Computers can't program themselves. All right, so let's I think I told you that that was the last one, right? I might have lied slightly because not meaning to do so, but it's just that while I was on a break, I looked at another problem which was too good to pass up on. So Let's do one last problem, and I promise it's the last one before we call it the day. All right, so here we have a nice graphic. Francisco needs to know the height of a tree, right here. From a given point on the ground, he finds that the angle of elevation to the top of the tree is 36.7 degrees. That's the given point. He then moves back 50 feet. And from this point, the angle of elevation is 22.2 degrees to the top of the tree. We want to then find the height of the tree. It's a really nice application, and it gets some interesting algebra in there, so I thought it would be very nice for you to see it. All right, and we are going to be using actually tangent quite heavily, aren't we? Because remember, we can write a couple of tangent statements here pretty quickly, because we have an angle, opposite side, and then adjacent side, right? H is what we're looking for, so tangent is preferred over cotangent. So here, notice that starting with the 36.7 degree angle, we can say that the tangent of 36.7 degrees equals opposite over adjacent, so h over x. Remember, this is a right triangle, so h over x, right? Which tells me if I cross multiply, h equals, remember, you can always put a 1 right there, h equals x times the tangent of 36.7 degrees. All right. Look at this other angle right here, 22.2 degrees. If I look at the tangent of 22.2 degrees, right? Again, if you feel like, oh, I see where he's going, let me go finish this myself, that would be a great idea, all right? If you can go and finish it off, you'll have done yourself a great favor. All right, so we get h over, that's called dynamic learning, right? Where you're not, or active learning, where you're not just passively sitting there and receiving information, you're actually fully participating in the obtaining of information. All right, so h over what? Well, let's see. For this larger triangle, the adjacent side is all of that. And how much is that? Well, there's 50 and there's x, and they need to be added. So x plus 50. So this tells me that if I, again, throw a 1 there and cross multiply, I get h equals x plus 50 times the tangent of 22.2 degrees, correct? Guess what? Both of these expressions are equal to the same thing. That means they must be equal to each other, right? So we get x tangent of 36.7 degrees equals quantity x plus 50 times tangent of 22.2 degrees. Now I need to go ahead and distribute the tangent of 22.2 degrees and solve for x, basically. So we get x times the tangent of 36.7 degrees equals x times the tangent of 22.2 degrees plus 50 times the tangent of 22.2 degrees. Now notice we're trying to solve for x. Keep your eye on the target. I see an x term here, one here, so we should get those on the same side. Let's do so. So we get x times the tangent of 36.7 degrees. I'm going to bring the one from the right to the left side, so it's going to become negative. So negative minus x tan 22.2 degrees equals 50 tangent of 22.2 degrees. All right, I hope now you realize why your algebra teacher kept telling you make sure you get your algebra down, because you're going to use it in every class from that point forward. All right, a lot of times what gets people in trig is not the trig, it's the algebra. All right, so notice that we're solving for x, so we need to get x by itself. Notice I have x in this term, x in that term. In other words, it's a common factor. So I'm going to go ahead and factor out the x. So I get x times tangent of 36.7 degrees minus tangent of 22.2 degrees equals 50 tangent of 22.2 degrees. We're almost done. All we're going to do now is divide both sides by this coefficient of x, and we'll be good to go. We just need to go ahead and plug it into a calculator. So we get x equals 50 tangent of 22.2 degrees divided by tangent of 36.7 degrees minus tangent of 22.2 degrees. Now we're going to carefully type that into our calculator. Let me move it over here and clear it. All right, so I'm going to put the numerator inside parentheses, so I have 50 times tangent of 22.2. As always, make sure you're in degree mode for the time being. Pretty soon we're going to switch over to radian mode. In fact, even as soon as our next video. So we get over this video. Basically, by the way, wraps up chapter 2 for us. So we're moving into chapter 3 starting with the next video. All right, so we get over tangent of 36.7. Make sure you exit the parentheses, and then minus tangent of 22.2 degrees. All right, and that should do it for us. So we see that x equals 60.4967, etc. Right now, I could round this, but if I want to get a really accurate answer, it's best that we round as little as possible. And also keep in mind, we're not solving for x, we're solving for h. Remember that h is x times the tangent of 36.7 degrees, right? So I know that this expression right here gives me x, right? So if I just take this expression and multiply it by the tangent of 36.7 degrees without doing any rounding, I'll get a really nice accurate answer. So let's try that. So let's bring that down and just multiply it right away by the tangent of 36.7. See, this is perfectly done because it is not doing any intermediate rounding, which is perfect because that gives you the best possible answer, most accurate possible answer. All right, so now we see that, right? And they want us to find the height to the nearest foot. in the instructions. So to the nearest 1 foot, notice that's a 0, so we can just drop all that. To the nearest foot, it's going to be around 45 feet. So we get h, which is x times tangent of 36.7 degrees, is almost 45 feet. All right, very nice problem, and notice how algebraically intense it was. So not difficult, but you do need to know what's going on, you know, at a very rudimentary level. All right, one thing to watch out for is make sure you don't stop there. You're not solving for x, you're solving for h, okay? And again, the great technique of not rounding till the very end. That's always, remember, the fewer times you round, the better your answer will be, the more accurate your answer will be. All right, so that should do it for this section. This should hopefully get you through the entire exercise set, which you should make sure you get done on time, and we will catch you during the next video. All right, stay safe till then.